Section 10.6 parametric equations. So far we've looked at equations that are considered to be rectangular equations, such as this one, y equals x squared, negative x squared over 72 plus x. So it's a function of x. And the difference between this type of normal equation that we're used to working with and a parametric equation is that this rectangular equation doesn't quite tell the whole story. So it does tell us where an object has been. So we're kind of saying that this is a trajectory of, let's say, a ball, right? So that kind of shape. And although that rectangular equation does tell us where the object has been, it doesn't tell us when the object has been. So for that, we can introduce a third variable called t, right? Which in this case would be like for time. And we can write both our x and y coordinates as functions of t, and that would give us what they call parametric equations. So in this case, we have two of them because we're only dealing with x and y in a plane space, right? If we were talking about 3D space, then you would have x, y, and z, right? So you can have more than two parametric equations depending on the situation. But here you see how they came up with parametric equation for x and parametric equation for y. And it's essentially the same graph as the one for the rectangular equation, but this does describe the movement to us. So this also has a direction, okay? So that's why here when you see it graphed, you not only see the shape of the graph, but also you see those little arrows. And that's because it's telling you the ball is traveling in that direction, right? If you're talking about a ball or whatever it is you're talking about in the moment. So notice time. So if I want to know, let's say these are seconds. So if I want to know where was the ball at 27 seconds, that's a lot, right? Maybe milliseconds. You would plug in 27 to your x parametric equation and to your y parametric equation to figure out the location there. So for a plane curve, we have x parametric equation and a y parametric equation because it's a two-dimensional space, right? As opposed to 3D, which is three-dimensional. T would be the parameter, so the third variable that we're using to make a function of t for x and a function of t for y. T would be the parameter. And the way you would sketch a curve is you could just use a table method. So given these two, for example, these two parametric equations, x is equal to t squared minus 4 and y is equal to t over 2. We do have a restrictions on t, right? Only from -2 to 3. So we can put values from -2 to 3 for the t column, and then we use those values to figure out the values of x and to figure out the values of y. Once you have those values, then you can plot the points, right? And then you can connect the dots from there. The arrows on the curve indicate its orientation. As t increases from -2 to 3, when a particle moves along this curve, it starts at the point 0, -1, and ends at the point of 5 3/2. Okay, so that's how we can kind of tell in what direction the arrows would go, right? It's based on the t, on the smaller t value going to the larger t value. And the only thing we're going to do here in this section, other than show you how the graphs work, is show you how to eliminate the parameter so that you can see a rectangular representation of the graph. So eliminating the parameter for a set of parametric equations is a pretty simple process. You have your parametric equations. You will solve for t in one of the equations. You will substitute it into the other equation, since there's two at least, and then you will get your rectangular version of the equation. Okay? So, for example, this is example 2. We have this set of parametric equations, 1 over square root of t plus 1, and y is equal to t over t plus 1. We will eliminate the parameter, and then we might also have to adjust the domain based on what result we get. So let's say we take the x equation, and we decide to solve this one for t. Right. If I want to get to the t, I'll need to get rid of that square root first of all. So one thing we can do to get rid of the square root is square it. So in this case, I'd have to square both sides of the equation to get x squared is equal to 1 squared is 1 over square root of t plus 1 times square root of t plus 1 will just be t plus 1. And then I want to get the t in the numerator, right? Because I'm going to solve for t, is our goal here. Solve for t. So what I can do here is just flip both sides. This is over 1. So if I flip both sides of the equation will still be intact. This would be 1 over x squared. This would be t plus 1. Then now it's easier to solve for t, right? I can just subtract 1 from both sides. So I would get t is equal to 1 over x squared minus 1. If I simplify a little further, just kind of put those two terms together. This would be 1 over x squared minus 1 over 1. If I get the same denominator, then I can use x squared as my common denominator. Which would give me 1 minus x squared. Like that. So t is 1 minus x squared over x squared. If I simplify this down to a single term. And then that chart they showed us earlier said solve for t in one of your parametric equations, and then plug that into the other equation, right? So in the other one we haven't used is our y parametric equation, y equals t over t plus 1. And now that we solve for t, we plug it into this second parametric equation. So we have y equals 1 minus x squared over x squared. That's my t on top over 1 minus x squared over x squared plus 1. Okay, something like that. Let's say I simplify that bottom part first. If I do a common denominator, this would be 1 minus x squared plus x squared, so this would just be 1 over, and then common denominator x squared. And then, of course, if I keep breaking this down, right, simplifying, the x squared that's in the denominator on top, and the x squared that's in the numerator on top, and then in the denominator on the bottom, those are going to cancel out. So I'm going to end up with this, which is just this. Like that. Okay, so that's our rectangular equation. That's how you eliminate the parameter t. So solve for t using one of the parametric equations, and then use that equation to plug it into the second one, and then simplify. This shows us that the graph is going to be a parabola, right? We have a x squared term. So it's a parabola that opens up or down. What do you think? Does this open up or down? Down because of the minus in front of the x squared, correct? And then the 1 would be like a y-intercept, right? We know because the y-intercept has a plus 1 here, we know that the graph would have the vertex at the point 0, 1. And also this rectangular equation is defined for all values of x. Because parabolas, when you draw them, right, they open up forever and ever. So we know that the way this equation is written, it technically has a domain of all real numbers, right, if we're talking about just the parabola itself. However, the parametric equations that we were dealing with when we started this are only defined for certain values. And let me put this over here. Oh, actually, let me go back up. So these were our original parametric equations. So one thing we have to watch out for is this square root in the denominator. The denominator cannot be 0, right? Ever. So this cannot be 0. But also inside here has to be greater than 0. So overall, this value just has to be greater than 0. Okay? So that's a restriction we have to worry about here. Square root of t plus 1 has to be greater than 0. Like that. What restriction does that have on t itself? If I square both sides, we would have t plus 1 greater than 0. T is greater than negative 1. This implies that we would restrict the domain of x to positive values only. So let me show you the pretty graph. So we got this parabola, right? We said it opens down. But if this was just a normal rectangular equation, we know it would be a two-pronged parabola, right, with a vertex at 0, 1. But because we got this from those parametric equations, there are other restrictions we have to worry about. So it would look like this. Okay, so just be aware that once you do the whole process of eliminating the parameter to get that rectangular equation, then you need to take a look also at the parametric equation you started with and see if there's anything that you need to worry about, right? In terms of what t can be, especially if you have a square root in the denominator. Really, the main things we worry about with domain are square roots or variables in the denominator. Let's move on to 4 here. So let's think about going backwards of what we just saw. Pretty straightforward. Find a set of parametric equations to represent the graph of y equals 1 minus x squared using each of these parameters. So they're giving us a rectangular equation here, and we're just going to rewrite it in parametric form. So we're going to do this twice, once with t equals x, and then another time with t equals 1 minus x. So if you notice, in the first one, if t is equal to x, then we know that x is equal to t. And then all we have to do is substitute t for the x's in our rectangular equation. So 1 minus x squared becomes 1 minus t squared. And then from there, there's nothing else to simplify, right? So those would be your two parametric equations for the equation we started with. X equals t and y equals 1 minus t squared. So it's that simple. But let's say they want you to let t equal 1 minus x. So similar, right? Just changes a little bit. If t is equal 1 to 1 minus x, then to get my x equation, I just have to solve for x, right? So solve for x. It's a minus x here, so you have to move the 1 over and then make the x positive. You end up with x is equal to 1 minus t. And then to find the y, you just plug in what x is equal to. So y is 1 minus x squared, so you would do, x is 1 minus t, so you would do 1 minus t squared. Okay? So 1 minus t squared, and then you just simplify this, and you get 2t minus t squared. So your parametric equations for part B would be x is equal to 1 minus t, and y is equal to 2t minus t squared. And those two would represent the rectangular equation that you started with. Okay? So it's pretty easy going the other way to get the parametric equations. Just plug in the parameters they're asking you to use. Right, so the first one, just use t for x, and then for the second one, you just use 1 minus x for t. So the first one is easy to find x, right? Because t is equal to x. But what is x? X is equal to t. T is equal to 1 minus x. So what is x? So here you do have to solve for x, right? But once you solve for x, then you take that value and plug it in here, your rectangular equation, and then just simplify. What is this? 71. X squared plus 1, we're going to do part B. So they want us to use t is equal to 2 minus x. Okay, so to find the x equation, parametric equation, we just solve for x. So we have t is equal to 2 minus x. So if I move the 2 over to the left, I can subtract. I get t minus 2 is equal to negative x. And then I can multiply by negative 1 on both sides to get a positive x. So this would be 2 minus t is equal to x, right? So that's our first parametric equation. And now that we know what x is equal to, we just take that and plug it into the rectangular equation they gave us. This is the rectangular equation. And if I plug in x, x will be 2 minus t squared plus 1. And then we just simplify. This will be what, 4 minus 2t minus 2t minus 4t plus t squared plus 1, which is t squared minus 4t plus 5. Okay, and those are our two parametric equations there. This is 17, eliminate the parameter. This is x parametric equation is 1/4 t, and the y parametric equation is t squared. So remember, you solve for t on one of them, and then you plug it into the other one, so that we end up with a rectangular equation. So if I solve for t in the first one, here I could just multiply by 4, both sides. T is equal to 4x. And then we take that and plug it into the other one. So we're going to have 4x squared, quantity squared, 4x quantity squared. So our rectangular equation here would be 4x times 4x, so we get 16x squared. Okay, so that's going from parametric to rectangular, and the other one was going from rectangular to parametric.